Some 40 years have passed since the birth of the first transistor. The period between that development and the appearance of today's VLSI chips was marked by amazing technical innovations. More than 300 VLSI chips can now be fabricated onto a single silicon wafer. The shimmering rainbow effect of the surface reflects points finer than 1 micron etched in high density. This is a microscopic view of a silicon chip only several millimeters square. The orderly lines and patterns on the surface look like a city map. Its integrated transistors exceed 1 million, with a total of 10 meters of interconnected wiring. The width of each line is less than 1 micron, considerably smaller than an amoeba. This phenomenal semiconductor technology is supported by countless related industries. This is a New Year's reception at a semiconductor plant where about 1,000 people have gathered. As many as 500 companies may be represented, all of which do business with the plant. After the official toasts, each group waits its turn to give New Year's greetings to the plant manager. Most of the participants then move to parties at other company plants. The firms represent more than 500 related fields, from the production of silicon material, gas, chemicals, and super pure water, to the numerous semiconductor manufacturing devices, all of which serve a single semiconductor plant. Moreover, each must be kept up to world standards. Located in the suburbs of Kita-Kyushu City in Fukuoka Prefecture is Mitsui High-Tech Incorporated, a little-known firm that enjoys a 30% share of the world's lead frame market. A lead frame is the small base on which a silicon chip is mounted when connecting gold wires to it. This is the material from which the lead frames are made. The roll is a long, thin metal alloy sheet of nickel and iron. One end is fed through the machine, a die is set in the punch press, and the thin sheet is punched at a rate of 1,500 times per minute. The founder and present chairman of the company, Mr. Takaaki Mitsui, was the first to realize that lead frames could be manufactured more cheaply using a die rather than an etching method.
When I founded the company, there were only 3 of us, myself and 2 employees. We had 3 vices and 6 hands in a tiny one-room workshop. That's how we began.
In 1949, when Mr. Mitsui began his business, Japan was struggling through a depression. The first thing he tackled was precision die technology using tungsten carbide. His success with this technology was the first in Japan. Orders poured in. The company grew. In 1968, Mr. Mitsui toured the United States. This is the U.S. Naval Air Station at Moffett Field in Silicon Valley. Mr. Mitsui visited here after learning that it was a center for new technology. The airfield is also home to NASA's Ames Research Center. Fairchild Semiconductor Corp is located nearby. During his visit, he spotted some small lead frames lying around.
I asked, "What on earth are these?" and was told they were lead frames for ICs. This was the first time I had heard the term IC. I then asked how much they cost and was amazed to hear that they went for $200 per 1,000 pieces. So I said, "I'll show you that I can make this thing for just 10 yen. But they looked as if what I was saying was just a lot of big talk.
Mr. Mitsui's first lead frames were so inexpensive that customers didn't trust them. But once Texas Instruments placed a huge order, Mitsui High-Tech grew rapidly. In this division, dies are manufactured according to customer specifications. This division processes the cutters to make the dies. And in this division, computers are employed to design the complicated cutters. Sales are now 30 billion yen annually.
If I hadn't come across those lead frames, our company's sales would at best be around 1 billion yen today. That we have become a firm with sales of 30 billion yen is without a doubt the result of my encounter with this new leading-edge IC technology. To be truthful, I didn't find this business because someone told me that there's this leading edge of industry somewhere out there. It was just a matter of chance. It was really nothing more than pure luck. It was just a fortunate occurrence.
30 minutes by freeway from San Francisco is the town of San Mateo. Every year, the Semicon West Show, a world-renowned exhibition of semiconductor-related technology, opens here. 1,000 companies from around the world participate in the three-day event, which is besieged by 50,000 people involved in the semiconductor industry. One-third of these visitors are from Japan. This polishing equipment gives silicon wafers a mirror-smooth finish, while this carrier handles wafers without human contact. This furnace diffuses impurities. This optical equipment transfers extensive patterns onto silicon, and another furnace grows crystals using chemical vapor deposition. 200 Japanese firms participate with American companies in many technological fields, such as bonding machines that connect gold wires to chips and semiconductor factory construction centering on clean rooms. The most advanced technologies in the world are gathered here to compete. There are several small and medium-sized businesses in Japan that have grown rapidly since entering the IC age. One such company is Disco Corporation. Disco has a 75% share of the world market for dicing machines. This is a diamond cutter that is attached to the rotary shaft of the machine. It is a mere 5 microns thick and cuts off more than 300 chips that are made on the surface of a silicon wafer. Powdered diamond is the raw material for the cutter. Ingredients other than diamond are a closely guarded secret. The ingredients are placed in a steel die, and an upper die ring is placed on top. The die is then put in a 200-ton press to harden the powder into ring form. This brown-colored cutter has been removed from the die after compression. In this state, it is approximately 1 millimeter thick. This is then hardened through baking while undergoing further compression. After baking for 3 hours at 800 degrees centigrade, the finished cutter is just 5 microns thick, the world's thinnest. To demonstrate, a strand of hair 0.2 millimeters or 200 microns in diameter is fixed to a base with paraffin. The cross-section of the hair is cut vertically and horizontally into 22 equal parts, which cannot be seen with the naked eye. Precision and minimum cutting width are the decisive productivity factors when chips are being sliced from silicon wafers. Before World War II, a Japanese naval arsenal was located at Kure City in Hiroshima Prefecture, where large numbers of grindstones were used to polish the gun barrels of warships. DISCO initially began as a small firm reconditioning these used grindstones. After the war, the founder of the firm, who had moved to Tokyo, purchased technology that mixes an abrasive with resin, flattening it into a thin disc and hardening it through baking to create a grinding wheel. This method produced what was then considered a super-thin grinding wheel with a thickness of only 140 microns. When mounted on a rotary shaft, this grinding wheel enabled the cutting of any number of items, large or small. Gradually, the focus of development shifted to the cutting of fine objects. In 1968, DISCO developed a cutter that was only 40 microns thick, which it immediately marketed to the semiconductor industry.
At that time, one large Japanese semiconductor firm and two American firms were making equipment using our cutters, but they couldn't cut properly. We were told that it was because the grinding wheels bent, and that it would be impossible to use them unless we made them stronger.
We then came to the conclusion that we had to make our own machine. We thought our product wouldn't be accepted unless a good special-purpose machine was especially made for it. But although we asked various machine tool manufacturers to take on the project, none would go out of their way to develop it for us.
It was in a rented warehouse in downtown Tokyo that DISCO developed its first dicing machine. This landmark equipment was eventually accepted worldwide, spurring the company's rapid growth. Without a machine to use them, DISCO would have been unable to sell its cutters. After independent experts were unable to make a suitable model, DISCO was forced to design and manufacture the device on its own. In 1975, the new machine was first unveiled at the Semicon West Show. This product resulted from a united effort by the company's new experts to develop a special-purpose machine for semiconductor use.
It was shoulder to shoulder in our corner all day. The American engineers had their eyes riveted on our machine. Since the outstanding feature of the DISCO machine was its cutting performance, we continued cutting without let-up. The worst point with the American-made dicing machines was that the grinding wheels broke soon after they started to cut. So we just kept cutting all day, day after day, to show off the durability of the DISCO grinding wheel. Normally in exhibitions like these, you don't display everything. This way, the weak points of your machine don't show that much. But it wasn't necessary to do that, since our machine was capable of safe, stable cutting. Day after day, we showed how a wafer could be cut sequentially, and in such small pitches that it was impossible to tell where the cutting had taken place. As a result, our dicing machine gained the reputation of being the one that kept on cutting without the grinding wheel breaking.
A dicing machine with a cutter that stays sharp. Eventually, this was equipped with a microcomputer and was finished into a completely automatic machine. The thin, durable cutter, plus the integration of precision machine and computer technology, made the equipment easier to use. DISCO's growth skyrocketed, and the company dominated the world market for a time. There are numerous fields in which the United States and Japan compete at the Semicon West Show, including bonding, in which chips sliced from wafers are connected to lead frames by thin gold wires. This bonder, made by Shinkawa Company, can connect 208 gold wire strands per minute. This machine, made by rival Kulik and Safa Industries, has the world's fastest bonding capacity, 304 gold wire strands per minute. Kulik and Safa has been the leader in the bonding field from the outset of the transistor age. With 1,000 employees and annual sales of 14.3 billion yen, the firm's bonders hold a 40% share of the world's market. This is Shinkawa, the first company in the world to automate the bonding process. With 300 employees and annual sales of 15 billion yen, it also holds a 40% share of the world market. Shinkawa, which was founded in 1959, began as a small transistor parts firm. This is an early model of its manually operated bonder. In transistor factories, connecting gold wires was the most labor-intensive process. Their bonders sold faster than the firm could make them. As a result, Shinkawa grew rapidly during the transistor boom.
Ultimately, the fact that a company's production volume depended on how many workers it could recruit came to be the popular belief. So everyone from chief clerks on up ran off to every corner of Japan and recruited workers from schools.
To guarantee their survival, Japanese semiconductor makers tried to secure the finest female factory workers. As school graduation approached, officials from semiconductor factories traveled the country to recruit girls from farming villages. Interviews began with a fingertip dexterity and eyesight test. Recruiters also looked for a sense of perseverance required for such repetitive work. Meanwhile, in the United States, Kulik and Safa had other concerns. Its problem was how to handle the thin, soft gold wire for easy movement to the bonding point. The answer was passing the tip of the gold wire through a fine glass tube, enabling it to be moved freely. This new method made it possible to greatly speed up the gold wire connection work, but the system still wasn't perfected. When a gold wire was accidentally pulled back into the glass tube, workers had to stop the production line to reinsert it. Kulik and Safa then devised ball bonding, a revolutionary method still in use. After the gold wire is connected to the terminal, it is then cut with an electrically generated spark. After the spark flies, the tip of the gold wire melts into a ball. This technology prevents the gold wire from being pulled back into the glass tube. However, America was slow to develop an automated bonding machine, and Japan was the first to complete the task. This bonding machine uses the latest technology. The equipment incorporates a large number of semiconductors, innumerable memory chips, and a high-performance microprocessor. After wages in Japan had risen, automation was the only alternative. Japanese engineers relied on the power of semiconductors. The appearance of the Intel 4004, the world's first microprocessor, provided that opportunity. This is a test-manufactured microcomputer using the Intel 8008 that was installed in this semi-automatic bonder. The bonder was improved until it was fully automated. The eyes, fingers, and patience of the female workers were no longer needed.
Shinkawa actually introduced automatic wire bonders before we did. The Japanese industry automated assembly before the American industry did. And that's because the American industry moved all its assembly to Southeast Asia. And because the labor rates were so low, they didn't care so much about automation. Japan being a higher labor cost area, they had to automate sooner. And I think that was an advantage for the Japanese industry. And certainly it was an advantage for Shinkawa. But we caught up to them in the late 70s and early 80s. And K&S and Shinkawa have been arch competitors ever since.
This is a microscopic view of a silicon wafer in which VLSIs have been etched. The wiring of the electronic circuits that can be seen here is only half a micron wide. The dust seen here straddling two wiring lines is the leading destroyer of microelectronic circuits. The modern semiconductor industry has been plagued by contamination such as dust and sodium ions. But the problem has been overcome. Since air along the coast contains a large amount of sodium, coastlines were considered unsuitable as sites for semiconductor factories. But in 1981, Sadakazu Shindo, who was chairman of Mitsubishi Electric Corporation, thought differently. For a number of reasons, Mr. Shindo decided to build a semiconductor plant at Saijo, facing Japan's inland sea.
We were living in a world where man had traveled to the moon, so it was stupid to think we couldn't build a semiconductor plant near the coast. I said that it definitely could be done, and they made it all happen. Maybe I was high-handed, but if you make the decision, you have to be high-handed in carrying it out.
At that time, we began talking about the dust problem at almost every meeting. Defects were occurring because of dust. In fact, workers were struggling with dust in all sorts of processes. But there was no one who attempted to carry out a systematic study of dust with accurate data. They were all saying the room was clean, but was it really? I wanted to find out. So I set up a machine called a dust counter to measure the dust level. I then carried out a variety of tests to see what happened when I changed my walking speed by walking slowly and even running. Actually, what I'm telling you is confidential, but I suppose it's all right because this happened 15 years ago. I also laid down and stood up and intentionally expelled cigarette smoke in the clean room to see how it moved. And I brought in mosquito coils and even made a video recording of how the airflow moves in the clean room. I really enjoyed these various experiments. All of them had a direct impact on product yields.
Mr. Fukumoto and his family brought a mannequin and clothes to dress it with to the seaside. They wanted to see how much sodium people's clothes absorbed from sea air. To measure this, clothes that had been washed in super pure water were put on the mannequin and left to stand for 3 days. The experiment showed that sodium is absorbed by 2 layers of clothing near the seaside. As a result of this experiment, it was decided that workers should change clothes before entering the factory.
To determine how much salt is excreted by the human body, my wife and I became the test subjects, since I couldn't ask others. We didn't bathe or change our underclothing for 3 days. This was to find out how much sweat clung to our underwear, our socks, undershirts, and so on.
Each member of the family wore 4 layers of underwear that had been washed in extremely pure water. They stopped bathing for 3 days to learn how sodium excreted by the body collected on the underwear. The samples from their underwear and bath water demonstrated the need for mandatory showers before entering the Saijo plant. Building a semiconductor factory near the sea presented many more problems, such as how to prevent salt-laden sea air from blowing into the plant. Layers of super high-performance filters were eventually perfected after trial and error experiments. For example, when the humidity was high, sodium that had been stopped by the filters melted due to the moisture in the air and penetrated through to the other side. This necessitated the development of a filter unit that would not allow water to pass through. It had to be structured so seawater sprinkled onto it like rain from the front wouldn't leak out from the rear. The unit was built and exposed to sea spray. An effective sodium blocking filter was eventually built.
4 companies were doing joint research, but only one worked seriously with us through to the end. We filed a joint patent with them. I've recently heard that buyers are even coming from overseas to purchase that company's filter. If they had done it together with us, I think the remaining 3 companies also would have made some profits. You know, there are a lot of stories like this when you talk about this kind of contamination. When things are clearly obvious and someone tells you you're no good, you work frantically to improve. But in areas where things aren't so obvious, the difference soon comes out between those who'll say they don't know what to do and those who'll seriously try to do something. Those who'll try to do something are the ones we need to handle such issues as preserving the earth. We can't expect any further progress with people who are satisfied with things as they are.
The device that reduces and transfers large, complicated circuit diagrams onto wafers is called a stepper. The light source is located in the upper part. The light that it emits passes through numerous mirrors until it focuses on the silicon wafer that comes in at the bottom. The blue light emitted from the ultraviolet lamp in the upper right-hand part passes through the lens, is bent at a right angle by the prism, and is sent through a vertically erected lens tube. In the center is a glass mask onto which a giant circuit diagram has been reduced and copied. The light beam passing through it focuses the image on the surface of the wafer after traveling through another lens. The stage moves length and crosswise. The light is synchronized so that the circuit diagram is copied in proper order onto the wafer. This is the stage onto which the wafers are placed. By matching the stage's movement with the timing of the light, the circuit pattern is copied over the entire surface of the wafer. The level of the stage must be extremely precise. It is placed on V-shaped grooves and is made so that it can move freely, lengthwise and crosswise. The surface of the V-shaped grooves must be precisely measured and polished perfectly. The polishing is done with a special grindstone technology so secret it can't be filmed. Although this worker is polishing with a cloth, this work also requires advanced technology.
This is a grindstone for finishing work. It's used to grind down the surface from a rough texture to a fine finish. As the grinding proceeds, the surface attains a mirror smoothness. If a portion is a little high, we use this small version to polish that spot away. I thought there wouldn't be much variation even if we did this work at ordinary temperatures. But when you start discussing 1 micron or 2 microns, or the sub-micron level of 0.2 microns or 0.3 microns, anyone saying, "Show me what you're doing here," for instance, throws off the machine's precision. When a person approaches, the temperature rises accordingly. Also, if you're working hard, your body temperature negatively affects precision. In a certain sense, you have to operate this machine on intuition, or knowing the knack of it, like in the old days. To run this machine requires special talent. This takes us into the realm of master artists, where you go by gut feeling.
Japanese do very delicate work, even for sub-micron processing. But Americans and Europeans don't try to do work when tolerances fall below 1 micron. It's not because they aren't serious about their work, it's that the differences can't be seen. Americans are clear about this because they talk about things quantitatively. If there's a standard, and if that standard can only be measured in microns, for instance, then measuring units below that is meaningless, because gauges and measuring devices give disjointed readings. Japanese, on the other hand, try hard to measure 0.2 microns, even under those circumstances.
Critics in the United States argue that Japan merely appropriated mainly U.S.-developed technologies for its own use. Although Japan may have refined those technologies, such critics say Japan has contributed very few major innovations. Further, they say that although Japan is outstanding when it comes to applying new technology to civilian use and mass producing it, it is rather weak when compared to the United States in creative research and development. The following two men who have watched Japan's semiconductor technology develop explain the respective differences.
The past 40 years of the semiconductor industry have been like climbing a mountain. The advanced nation of America started up the mountain, ahead of Japan, and slipped and fell. We learned from their experience. In other words, Japan was able to progress without wasting efforts. Another important thing is that the speed at which America is climbing has slowed. This isn't because America is lazy, but that its technology is now mature. When you enter the age of maturity, the more developed the country, the harder things become. When the technology matures, the research and development expenses progress one step further and increase enormously. The further ahead you are, the more you lose. America has undergone this hardship. Therefore, when you consider the path that we have traveled, I think that the historical circumstances in which Japan was placed and the characteristics of Japanese society have reinforced each other, leading to amazing progress in Japan's semiconductor industry.
As Japan has become so prosperous, it is now burdened with the duty of creating future products on its own. Development costs money. Since the Japanese have relied on others up to now, a backlash has occurred. But the Japanese have made a very big contribution by spreading inexpensive, high-quality products throughout the world. Society, however, cannot progress only through copying. From now on, I think that Japan should give careful consideration to environmental problems while carrying out industrial development in areas that humanity will require in the future.